Imagine you've built a new restaurant booking app and it suddenly goes viral. It's Friday night, the clock strikes 6, and thousands of reservations start flooding in at the exact same moment. You might expect to celebrate, but instead, the screens freeze. The entire app crashes. The database simply couldn't save that much incoming data all at once. To understand why, we have to look at how a standard database saves information. To update a customer's record, the system has to physically search the hard drive, find the exact file where that user lives, and overwrite it. Engineers call this a random write. Think of it like a clerk running into a massive filing room, hunting down one specific folder, writing a note, and running back out. Doing that once is fine, but when thousands of users try to do it simultaneously, the sheer mechanical effort creates a bottleneck, bringing the whole system to a halt. So how do we fix this? What if we stopped searching for old folders entirely and instead just scribbled every new booking at the very bottom of a running list? Because the computer never has to waste time searching the drive, writing data this way is incredibly fast. You just drop the new information at the end of the line and immediately move on to the next user. But this animation shows the fatal flaw of the idea. If you need to look up a specific reservation in this long scrolling list, you have to read it line by line from the very top to the bottom until you spot the right name. This is the core dilemma for engineers. You can either have lightning-fast saving by adding to a list, or lightning-fast searching by keeping things meticulously organized. Doing both at the same time seems impossible. To solve this, we can look at this split-screen diagram. It divides the computer into two parts: fast temporary memory on the left, called RAM, and slower permanent storage on the right, the disk. Instead of sending new bookings straight to the slow disk, we catch them in RAM first. Think of this space like a restaurant host's podium. It acts as a quick scratch pad to catch the chaotic rush of incoming requests. Because RAM is electronic and extremely fast, this podium scratch pad, often called a mem table, instantly sorts those bookings alphabetically by the customer's name the moment they arrive. By catching and organizing the data in memory first, the system easily absorbs massive spikes in traffic without ever touching the slower hard drive. But memory is temporary. If the server loses power, the scratch pad is wiped clean. It also has limited space. So what happens when our podium gets full? Watch this diagram as the perfectly sorted list from the RAM side slides over to the disk side. It's saved in one quick, continuous motion as a solid block, known as a sorted string table, or SS table. Once that block is written to the disk, it is locked. It is permanent, and it can never be modified. If someone cancels a reservation, the system doesn't waste time hunting down their old file on the disk to erase it. Instead, it just drops a new cancellation note, often called a tombstone, into the fast, active scratch pad on the left. By organizing everything in fast memory and saving it in solid, locked blocks, we've entirely eliminated the need for those slow, mechanical random writes. Now, when a customer walks in and you need to look up their table, the system checks the fast scratch pad first. If the name isn't there, it checks the absolute newest locked block on the disk. If the name still isn't there, it simply steps backward in time, checking the next older block and the next until it locates the record or confirms the person never booked. Summing up, we've made a calculated trade. Saving data is practically instant, but reading it means we might have to glance at a few different lists. Over time, there is a consequence to this setup. Appending all these new blocks and cancellation notes creates an unsustainable, cluttered pile of files on the disk, which makes searching slower and slower. To stop the drive from overflowing, the database runs an automated background sweeper process called compaction. This technical diagram shows exactly how that works. The system takes several old segments, merges them together, throws away the canceled or deleted data, and outputs one clean, consolidated segment. This routine maintenance keeps the reading process fast and prevents the storage drive from running out of space. This entire ecosystem, the memory scratch pad, the locked disk blocks, and the background compaction, forms an elegant structure known in engineering as the log-structured merge tree. It purposefully accepts a little bit of extra searching and background chore work in exchange for the incredible ability to absorb incurring data at maximum speed. So the next time your app experiences a massive surge of users, the server won't buckle under the weight. Behind the scenes, this architecture is quietly sorting the chaos.
ensuring every single action is saved when it matters most.